Welcome to this session on CCNA tutorial, Network Fundamentals. This video is aligned with Cisco's official CCNA 200-301 exam blueprint and is designed to guide you step-by-step toward certification success. In this video, we're covering the entire Section 1, Network Fundamentals, combining everything from 1.1 to 1.13 in a single overview. If you prefer shorter, focused lessons, each subtopic also has its own 10-minute video. Here, we'll look at the core components that make up a network, the topologies they use, and the physical cabling that ties everything together. We'll walk through IPv4 and IPv6 addressing, TCP versus UDP, wireless principles, virtualization fundamentals, and the essential switching concepts like MAC learning, frame forwarding, and flooding. Let's get started. Section 1.1. Role and function of network components. Endpoints, or end devices, are the computers, phones, printers, and IoT devices that people interact with directly. They sit at the edge of the network and either generate or receive data, but they do not forward traffic like switches or routers. The purpose of endpoints is to give users access to the services and applications they need, whether that's checking email, making a VoIP call, or streaming video. Endpoints come in many forms. They include personal devices like laptops, desktops, and smartphones, office devices like printers and IP phones, and even specialized equipment like CCTV cameras or IoT sensors. Each endpoint connects to the network through a NIC, which provides a unique MAC address and is assigned an IP address for communication. In practice, endpoints generate traffic when they send requests and consume traffic when they receive responses. They rely on intermediary devices to move that data across the network, but they remain the ultimate source and destination of all communication. Network Interface Card. A network interface card, or NIC, is the component that allows a device to connect to a network. It may be a physical adapter, such as an Ethernet port or a wireless card, or a virtual adapter inside a virtual machine. The NIC's purpose is to provide the bridge between the device and the network so that it can send and receive data. Each NIC has several important features. It always provides a unique MAC address for identification at Layer 2 and supports the assignment of IP addresses for communication at Layer 3. NICs can be wired or wireless, physical or virtual, and support different speeds and duplex modes depending on the hardware. In operation, the NIC handles the transmission and reception of frames, encapsulates and decapsulates data, and ensures error detection and flow control. It works with the operating system to bind MAC and IP addresses, allowing applications and users to reliably communicate over the network. Servers are computers built to provide services and resources to many clients at once. Unlike a laptop or desktop, which is optimized for a single user, a server is designed to handle multiple requests simultaneously. The purpose of a server is to centralize applications and data so that users can reliably access what they need over the network. Servers have several important features. They can be physical machines in a data center, virtualized systems running on hypervisors, or cloud-based platforms. They run specialized operating systems that support scalability, reliability, and security. Servers may be dedicated to a specific service, such as DHCP or DNS, or they may provide multiple services at once. In operation, servers perform many critical functions. They can assign IP addresses with DHCP, resolve names with DNS, host websites and email, authenticate users, and store files. Whether on-premises or in the cloud, servers are essential for keeping networks and business applications running smoothly. Switches. A switch is a device that connects multiple devices within a LAN and forwards traffic using MAC addresses. Unlike hubs, which send data to every port, a switch sends traffic only to the correct destination. Its purpose is to make LAN communication faster, more efficient, and more reliable by reducing collisions and keeping traffic organized. Switches provide important capabilities. Each port is its own collision domain, and full duplex communication allows data to flow in both directions. VLANs segment the network for performance and security, while port security restricts unauthorized access. Managed switches add scalability and can be configured or monitored through CLI or GUI. Switches learn MAC addresses from incoming frames, record them in a table, and forward traffic only where it needs to go. If the destination is unknown, the switch floods the frame until the address is learned. They also filter unnecessary traffic, and Layer 3 switches can route between VLANs. A router is the device that connects separate networks and forwards traffic using IP addresses. While switches organize communication inside a LAN, routers make sure data can leave the LAN and reach other networks, including the Internet. Their purpose is to enable inter-network communication and guide data along the best available path. Routers have several important features. They operate at Layer 3 of the OSI model and rely on routing tables to make forwarding decisions. They support both IPv4 and IPv6 and can be configured with static routes or use dynamic routing protocols like OSPF or EIGRP. Routers also provide services such as NAT to translate private addresses, ACLs to filter traffic, and QoS to prioritize critical applications. In operation, routers learn about local and remote networks, build and maintain a routing table, and forward packets based on the destination IP. They select the best path using prefix matching and metrics, while also filtering or translating traffic when needed. Power over Ethernet, or PoE, is a technology that allows a single Ethernet cable to carry both data and electrical power. This means devices such as access points, IP phones, or security cameras can operate without a separate power source. The purpose of PoE is to make deployment easier and more flexible, especially in locations where it would be difficult or expensive to install power outlets. PoE has a number of key features. It follows IEEE standards such as 802.3 AF, which provides up to 15 watts, 802.3 AT PoE+, which supports up to 30 watts, and 802.3 BT, also called UPoE, which can deliver up to 60 or even 100 watts. Many modern switches include built-in PoE capability, which lets administrators power devices directly from the switch and manage power centrally. In operation, a PoE-capable switch detects whether a device requires power, negotiates the correct level, and supplies it safely. This reduces cabling, simplifies installation, and allows devices to be placed exactly where they are needed. Access points are the bridge between wired and wireless networks. They allow laptops, phones, and IoT devices to connect without cables. On their own, APs can provide connectivity, but in larger environments, they are managed by a wireless LAN controller. The purpose of the WLC is to centralize configuration, security, and monitoring. APs and controllers have several important features. They can support multiple SSIDs linked to VLANs, apply security through WPA2 or WPA3, and enforce policies for traffic such as voice or video with QoS. In practice, access points connect wireless devices to the LAN, convert wireless frames into Ethernet frames, and enforce encryption and authentication. With a WLC, they can also provide seamless roaming, apply advanced policies, and give administrators centralized visibility and control over the wireless network. Next-generation firewalls and IPS are designed to address the limitations of traditional firewalls. While older firewalls mainly filter by IP, port, and protocol, next-generation firewalls can recognize applications, users, and traffic patterns, giving administrators much greater visibility and control. Their purpose is to defend against modern cyber threats while enforcing detailed security policies. Key features of next-generation firewalls include application awareness, user-based policies, and built-in IPS capabilities for real-time threat prevention. They also support SSL TLS inspection, allowing encrypted traffic to be analyzed, and often provide integrated VPNs, URL filtering, and centralized reporting. In operation, next-generation firewalls filter and inspect traffic at multiple layers, block known attack signatures, and analyze traffic behavior to stop intrusions or malware. They can enforce policies for specific applications, such as allowing business tools while restricting non-work traffic. By combining firewall and IPS functions, next-generation firewalls deliver stronger, more flexible protection for today's enterprise networks. Section 1.2. Network Topology Architectures. The two-tier architecture is a simplified network design made up of the access layer, where end devices connect, and the distribution layer, which aggregates those connections. Its purpose is to provide a straightforward, cost-effective way to structure small to medium-sized networks. This design is easy to manage and deploy, requiring fewer devices and less complexity. Key features include VLAN segmentation, policy enforcement at the distribution layer, and simple inter-VLAN routing if distribution switches operate at layer 3. It is less scalable than larger models, but ideal for environments where growth is limited. In operation, the two-tier design connects users through access switches and forwards aggregated traffic to the distribution layer for policy decisions and routing. Common use cases include branch offices, schools, and mid-size enterprises, where simplicity, lower cost, and easier management outweigh the need for high scalability. The three-tier architecture builds on the two-tier model by adding a core layer on top of access and distribution. Its purpose is to provide scalability, resilience, and high-speed connectivity for large enterprise networks. This model is modular and fault-tolerant. The access layer connects devices. The distribution layer aggregates and enforces policy, and the core acts as a high-speed backbone. In practice, the three-tier model separates local access traffic from backbone traffic, ensuring performance and fault isolation. It is widely used in corporate headquarters, university campuses, and large enterprises where growth, high availability, and performance are critical. Spine leaf is a modern data center design where every leaf switch connects to every spine switch. Its purpose is to provide predictable, low-latency paths for workloads that generate heavy server-to-server communication. The design is highly scalable and balances traffic evenly across the spines. Each device has the same number of hops to reach another, which guarantees consistent latency. Key features include modular growth, horizontal scalability, and optimization for east-west traffic. SpineLeaf provides large data centers with fast, balanced communication between servers and applications. Use cases include cloud providers, virtualization-heavy enterprises, and environments that demand predictable performance for distributed workloads. A wide area network, or WAN, connects multiple LANs across geographic distances. Its purpose is to enable secure communication between branch offices, headquarters, data centers, and the cloud. WANs rely on service providers and technologies such as MPLS, leased lines, or site-to-site VPNs. They are more expensive than LANs, can introduce latency, and require careful planning. In operation, WANs extend enterprise connectivity globally and provide secure inter-site communication. Use cases include retail chains connecting branches to HQ, enterprises accessing cloud applications, and organizations setting up disaster recovery sites. SOHO networks are designed for small offices or home users, providing basic connectivity at low cost. Their purpose is to give users reliable access to the internet and local resources with minimal complexity. These networks usually run on consumer or small business equipment, often a single, all-in-one device combining routing, switching, Wi-Fi, and firewall functions. They are cost-effective, simple to configure, but limited in scalability and advanced features. SOHO networks provide wired and wireless connectivity, basic firewall protection, and NAT for internet access. Common use cases include remote workers, startups, and small branch offices where ease of use is more important than enterprise-grade scalability. On-premises networking means infrastructure is hosted and managed locally, while cloud networking relies on provider-managed resources. The purpose is to give organizations flexibility in where and how services are deployed. On-premises offers full control and data sovereignty, but requires higher capital investment. Cloud provides scalability, agility, and reduced management overhead, but depends on internet connectivity and provider trust. Hybrid models combine both for balance. On-premises suits compliance-heavy industries like banking or government. Cloud fits startups, SaaS applications, or organizations needing rapid scaling. Hybrid environments are now the most common, blending control with flexibility for modern enterprises. Section 1.3. Physical interface and cabling types. Single-mode fiber, or SMF, is an optical fiber with a very narrow core of about 9 microns. Its purpose is to carry light signals across very long distances with minimal loss, making it ideal for wide area and backbone networks. It uses laser light as the transmission source and supports very high bandwidth. Because only one light path travels down the fiber, it avoids modal dispersion, resulting in cleaner signals. Typical wavelengths are 1310 or 1550 nanometers, and distances can extend for tens of kilometers. However, transceivers for SMF are more expensive, and installation requires precision. In operation, single-mode fiber enables long-haul communication, such as telecom backbones, inter-building connections on campuses, and links between data centers. Compared to multimode or copper, it provides higher performance and longer reach, though at a higher cost. Multimode fiber, or MMF, is an optical fiber with a much larger core, typically 50 or 62.5 microns. Its purpose is to carry multiple light paths, or modes, making it suitable for short to medium distances at lower cost compared to single-mode fiber. It uses LEDs or low-cost lasers like VCSELs as light sources. Because multiple light modes travel through the fiber, it is more prone to modal dispersion, which limits distance. Typical ranges are up to about 550 meters for gigabit Ethernet, and less as speeds increase. Multimode fiber operates at wavelengths of 850 or 1300 nanometers, and is generally cheaper than single-mode fiber, both in equipment and installation. In practice, multimode fiber carries multiple light signals simultaneously, providing reliable and affordable connectivity for shorter links. It's widely used in local area networks, inside buildings, and in data centers, especially for backbone links that don't require very long distances. Copper cabling transmits data using electrical signals over twisted pair or coaxial cables. Its purpose is to deliver cost-effective and flexible connectivity for local area networks and access networks. Copper cabling includes unshielded twisted pair, shielded twisted pair, and coaxial designs. Standards like Cat5e, Cat6, and Cat6a define bandwidth and performance. The maximum length for Ethernet over twisted pair is 100 meters. Copper is more susceptible to electromagnetic interference than fiber, but it is inexpensive, easy to install, and supports power over Ethernet for end devices. Copper is widely used to connect end devices, like computers, phones, and printers within LANs. It is the most common cabling inside buildings, used in patch panels and wall drops. While limited for long-distance backbones, copper excels in affordability, ease of deployment, and PoE functionality, making it the default choice for access networks. Single mode supports the longest distances, up to hundreds of kilometers, but comes with higher costs due to laser optics. Multi-mode is more affordable and works well for shorter runs within LANs and data centers. Copper is the lowest cost and limited to 100 meters, but it's widely used for in-device access and supports power over Ethernet. Each medium balances distance, cost, and use cases differently, making the right choice critical for network design. The standard SFP supports 1 gigabit, while SFP Plus increases that to 10 gigabits. SFP28 handles 25 gigabits, and QSFP modules scale higher, with 40 and 100 gigabit options. The QSFP-DD can push up to 400 gigabits. All of these transceivers can operate over copper or fiber optics, giving flexibility depending on distance and design. Choosing the right SFP depends on the bandwidth needed and whether the link is short-range copper or long-haul fiber. Ethernet connections can be based on shared media or point-to-point links. Shared media allows multiple devices to use the same communication channel, while point-to-point provides a direct link between two devices. The purpose is to highlight how connection types influence network performance. In shared media, devices contend for access, collisions occur, and half-duplex is typical. This was common with hubs and coaxial cables. Point-to-point connections, on the other hand, use dedicated bandwidth between two devices, enable full duplex operation, and eliminate collisions. Switch-based Ethernet is now the standard, making point-to-point the norm in modern networks. Shared media was used in early Ethernet LANs but is largely obsolete today. Point-to-point dominates in current networks, connecting switches to hosts and other switches, ensuring efficient, reliable, and scalable communication. It is the foundation of enterprise and data center connectivity. Section 1.4. Identify interface and cable issues. Collisions occur when two Ethernet devices transmit at the same time on the same medium. This was common in legacy hub-based or half-duplex networks, but should never happen in modern full-duplex switched Ethernet. Collisions happen because multiple devices compete for the same collision domain, and CCNA/CD has to stop and retransmit after a random delay. You'll know there's a problem if collision counters in show interfaces increase, performance slows down, or retransmissions become frequent. A healthy full duplex link should show 0 collisions. If collisions appear, the solution is to eliminate hubs, configure full duplex correctly, or replace faulty NICs. Errors represent abnormal frames that violate Ethernet standards. A CRC error means the checksum failed, showing corruption in transit. Runts are frames smaller than 64 bytes, often caused by collisions or duplex mismatches. Giants are frames larger than 1,518 bytes, usually due to MTU mismatches or faulty NICs. You'll see these as input errors in show interfaces. If CRC, runts, or giants increase, expect packet loss and poor throughput. A clean interface should always report 0. Fixes include replacing or rerouting bad cabling, reducing EMI interference, correcting MTU settings, and checking duplex consistency. A duplex mismatch happens when one side of a link runs full duplex, while the other side is half duplex. This typically occurs when one end is hard-coded and the other is left to auto-negotiate. Auto-negotiation defaults to half duplex if it can't detect partner settings, causing the mismatch. The result is very slow throughput, CRC errors, and late collisions. Cisco devices often warn you with a duplex mismatch message. In show interfaces, you'll spot half duplex paired with errors. The fix is to configure both ends consistently. Ideally, use auto-negotiation on both, or hard set both ends the same. Speed mismatches occur when two ends of a link are configured with different speeds. For example, one end forced to 100 megabits per second and the other on auto. Or, one device only supports fast Ethernet while the other is gigabit. When speeds don't align, the link may fail to come up at all, flap repeatedly, or run very poorly. In show interfaces, you'll see line protocol down if the speeds don't match. To resolve, make sure both ends use the same speed, or better yet, leave both set to auto. Also confirm hardware supports the desired speed. Here you can see a summary of what we've already covered, so just use it as a quick reference during review. The exam will often give you a snippet of show interfaces and ask you to identify the problem based on these counters. The key rule is on a healthy link, these counters are always 0. Any increase means something is wrong, and the type of counter tells you exactly where to look. When scanning show interfaces in the exam, use a fast checklist. First, check the interface status. Is it up/up? Next, verify duplex and speed. Then scan for non-zero counters, like collisions, CRCs, runts, giants, or late collisions. Confirm that reliability is at 255 out of 255. Finally, check for drops or resets. If any of these fields don't match the expected healthy values, you've found the anomaly. That's exactly what the CCNA exam is testing: your ability to spot what stands out in a long iOS output. Section 1.5. Compare TCP to UDP. TCP, or Transmission Control Protocol, is a connection-oriented protocol that operates at layer 4 of the OSI model. Its primary role is to ensure reliable, ordered delivery of data between applications. making it essential for accuracy-critical processes like web browsing, file transfers, and email. TCP's reliability comes at the cost of extra overhead because of its larger header. It's commonly used for web browsing with HTTP or HTTPS, file transfers via FTP, email services such as SMTP and IMAP, remote access tools like Telnet and SSH. TCP windowing is the mechanism that controls how much data a sender can transmit before waiting for an acknowledgement. It ensures the sender does not overwhelm the receiver while keeping data flowing efficiently. During the initial handshake, the acknowledgement is always the sequence number plus 1, since the scene flag consumes one sequence number. Once data transfer begins, the sequence number increases by the number of bytes sent, and the acknowledgement reflects the last received byte plus 1, confirming that all data up to that point has been received successfully. Here's an example of how this works with a window size of 3,000 bytes. Host A sends 3 packets of 1,000 bytes each. The sequence numbers start at 1 and advance to 1,001, then 2,001, and finally 3,001, filling the window. Host B acknowledges with ACK 3001, confirming receipt of all data up to byte 3000. This frees the 3,000 byte window so host A can continue sending. If packet 2 is lost, host B continues to send ACK 1001, waiting for the missing data. The window will not slide forward until the packet is retransmitted. UDP, or User Datagram Protocol, is a connectionless protocol. It provides best effort delivery, meaning there's no guarantee that packets will arrive or be in order. It prioritizes speed and efficiency, making it ideal for real-time applications where a small amount of data loss is acceptable. Because of its speed, UDP is commonly used in DNS and DHCP, where small, quick queries matter. In VoIP and video streaming, where slight data loss is acceptable, and in online gaming, where latency directly affects performance. Here's a direct comparison between TCP and UDP. TCP provides reliable, ordered delivery using features like sequencing and acknowledgements. UDP is fast and lightweight, but with no reliability or ordering. Choose TCP when accuracy is essential, like in web browsing or file transfers. Choose UDP when speed matters most, like in streaming or gaming. Section 1.6. Configure and verify IPv4 addressing and subnetting. IPv4 is a 32-bit addressing system that uniquely identifies devices on a network. It's written in dotted decimal format, like 1.2.3.4. Each address is split into a network part and a host part, based on the subnet mask. Computers work with binary, but we use decimal to make it easier for humans. Each octet has 8 bits, and each bit has a value that doubles as you move left. Starting from the right, the values are 1, 2, 4, 8, 16, 32, 64, and 128. That's why binary aligns so perfectly with IP addressing. To convert decimal to binary, start with the largest bit value, which is 128. If the number is at least that big, put a 1 and subtract. If not, put a 0. Then move to the next bit. If the remainder is 0, the rest are all zeros. For example, with 160, it's larger than 128, so we put a 1 and subtract 128, leaving 32. Then move to the next bit, 64. 32 is smaller than 64, so we put a 0 and move to the next bit. 32 is exactly the next bit value, so we put another 1 and subtract. Now the remainder is 0, so the rest are all zeros. The binary result for 160 is 101, followed by 5 zeros. To go from binary to decimal, line up the bit values and add up only the ones that match a 1. For example, if the first 2 bits are 1s, that's 128 plus 64, which equals 192. If all 8 bits are 1s, the total is 255. A subnet mask separates the network portion from the host portion. It's always written as 1s followed by zeros. For example, 255.0.0.0 is a /8 because the first 8 bits are zeros. The mask tells us the network ID, the host range, and the broadcast address. The network portion identifies the subnet. It's the same for all devices in that network and shown as ones in the subnet mask. The host portion identifies the specific device. It's unique for each host and shown as zeros in the subnet mask. Think of it like a street name and a house number. The subnet mask decides where the split happens. Ones mark the network part, and zeros mark the host part. For example, for a /16 subnet mask, the first 16 bits or ones define the network, and the rest identify the hosts. The network address or network ID is the first address in a subnet. All host bits are set to 0. It identifies the entire subnet and can't be assigned to a device. Routers use it to route traffic between networks. To calculate it, perform a logical AND between the IP address and the subnet mask. Wherever the mask has a 1, keep the IP bit. Wherever it has a 0, replace it with 0. For example, with 1.1.1.1/16, the mask is 255.255.0.0. Applying the AND operation gives 1.1.0.0, which is the network address, the starting point of that subnet. The broadcast address is the last address in a subnet, where all host bits are set to 1. It's used to send a message to all devices within that subnet at once and can't be assigned to a host. To calculate it, keep the network bits the same and set all host bits to 1. For example, with 1.1.1.1/16, the broadcast address is 1.1.255.255, the final address in that subnet. The usable hosts are all the addresses between the network ID and the broadcast address. To find the usable range, simply add 1 to the network ID to get the first usable host, and subtract 1 from the broadcast address to get the last usable host. For example, if the network is 1.1.0.0/16, the broadcast address is 1.1.255.255. That means the first usable host is 1.1.0.1, and the last usable host is 1.1.255.254. Every address between those two can be assigned to devices inside that subnet. Subnetting is the process of dividing a large network into smaller and more manageable subnetworks. We do this by borrowing bits from the host portion of the address and turning them into network bits. The main goal is to use addresses more efficiently, reduce broadcast traffic, and improve performance and security. When we borrow bits from the host portion, we create more subnets. The number of subnets equals 2 raised to the power of the number of borrowed bits. For example, imagine a network 1.1.0.0/16. If we borrow 2 bits, the new prefix becomes /18. Now we have 4 smaller subnets instead of 1 large network, each with its own network ID, host range, and broadcast address. When you need to create a specific number of subnets, follow 3 steps. Step 1. Check how many subnets are required. Step 2. Find the smallest power of 2 that is greater than or equal to that number. Step 3. Add that number of borrowed bits to the original prefix to get your new subnet mask. Let's go through an example. We want to divide a /8 network into 3 subnets. We test powers of 2. 2 to the power of 1 equals 2, which is not enough. 2 to the power of 2 equals 4, which covers the requirement. So we borrow 2 bits, giving us 4 subnets in total. The new prefix becomes 8 plus 2, which equals /10. That's how we find the number of borrowed bits and the new subnet mask. To find out how many hosts each subnet can support, we use this simple formula. 2 raised to the power of host bits minus 2. The minus 2 is important. We remove 1 address for the network ID and 1 for the broadcast address. Let's look at an example. If we have a /24 network, there are 8 host bits left. 2 to the power of 8 equals 256. And after subtracting 2, we get 254 usable hosts. When you're asked to design a subnet for a specific number of hosts, the goal is to find the smallest subnet that can fit them all. Use the formula 2 raised to the power of host bits minus 2, and test until the result meets or exceeds the required number of hosts. For example, if we need at least 100 hosts, 2 to the power of 6 equals 64, which is too small. 2 to the power of 7 equals 128, which is enough. That means we need 7 host bits. Now, to find the prefix, subtract 7 from 32. 32 minus 7 equals /25. A /25 subnet supports 126 usable hosts, which is more than enough for 100 devices. The block size shows how big each subnet is and how much we count up to reach the next one. We find it by raising 2 to the power of the number of host bits. In a /25 network, the subnet mask is 255.255.255.128, which gives a block size of 128. This means network IDs appear at multiples of 128 in the last octet, 0 and 128. The first subnet runs from 0 to 127, and the next starts at 128 and ends at 255. Each subnet provides 126 usable host addresses. Variable length subnet masking lets us create subnets of different sizes instead of equal ones. For example, from a /24, you could create a /25 for 100 users, a /27 for 25 users, and a /30 for a point-to-point link. Section 1.7. Private IPv4 addressing. Before CIDR was introduced, IPv4 addresses were organized into 5 classes, A through E. These classes help define how many bits belong to the network portion and how many to the host portion. The idea was to make IP allocation and routing simpler in the early internet days. Class A addresses always start with a 0 in the first bit, meaning the first octet ranges from 0 to 127. The default subnet mask is 255.0.0.0. That's a /8 prefix. It supports 128 networks with up to over 16 million hosts per network. So these are built for very large organizations or ISPs. Class A networks are designed for massive scale, like internet service providers, or large tech companies like Google or Apple. They use it where millions of devices need unique IP addresses within a single network. An example is the public address 12.0.0.1, or the private address 10.0.0.1. Class B addresses start with the binary pattern 10, giving a first octet range from 128 to 191. Its default subnet mask is 255.255.0.0, or /16. This provides a balance: 16,000 networks, each with 65,000 hosts. Perfect for medium-sized organizations. Class B offers a good middle ground. Not too big, not too small. It's commonly used in universities, large corporations, and regional networks. A common private range here is 172.16.0.1 through 172.31.255.254. Class C addresses start with the bits 110, covering 192 to 223 in the first octet. The default mask is 255.255.255.0, or /24. Each network supports up to 254 hosts, ideal for small networks and offices. Class C provides many small networks, making it great for LANs and small enterprises. Most home and small office routers use this range. For example, 192.168.1.1. Public examples include addresses like 203.0.113.10. Class D addresses begin with 1110, so their range is 224 to 239. These are not used for regular unicast traffic. Instead, they're reserved for multicast communication. That means one sender can deliver data to multiple receivers at once, used by routing protocols like OSPF or for streaming applications. Common examples include OSPF, which uses 224.0.0.5, and RIP, which uses 224.0.0.9. They're also used in video conferencing, IPTV, and multicast DNS. Class E addresses start with 4 ones and cover 240 to 255. These are reserved for experimental or research use by organizations like the IETF. You won't see them in production networks. They're strictly for testing or protocol development. Class E addresses are mainly used in lab environments for protocol testing, simulations, or IETF experiments. An example is 240.0.0.1, a non-routable address reserved for research. Here's a quick visual summary. Each class starts with a specific binary prefix, 0 for Class A, 10 for Class B, and so on. This prefix decides how many bits belong to the network versus the host portion. Before CIDR, this was how networks were divided and routed. Each IPv4 class starts with a unique binary prefix that defines its range. Class A begins with a 0, covering 0 to 127. Class B starts with 10, that's 128 to 191. Class C uses 110, or 192 to 223. Class D begins with 1110 for multicast, and Class E with 1111 for experimental use. So those leading bits decide the class and address range. In classful addressing, the first few bits of an IP identify the class, and that pattern decides how many bits belong to the network and how many to the hosts. In Class A, 8 bits are for the network and 24 for hosts, allowing over 16 million hosts per network. Class B splits it evenly, 16 and 16, about 65,000 hosts. And Class C uses 24 network bits and 8 host bits, giving 254 usable addresses. So the more bits you allocate to the network, the fewer hosts each subnet can support. Now let's move to private IPv4 addressing. Private IP addresses are ranges defined by RFC 1918 for use inside local networks. They're not routable on the public internet and must go through NAT, Network Address Translation, to access external networks. The goal is to save public IPv4 space, enhance security, and allow organizations to reuse the same ranges internally. Private IP addresses are used only inside local networks. They aren't routable on the internet and need NAT to reach external sites. Any organization can reuse them without registration, and they add a layer of security by isolating internal devices from the public internet. There are 3 private IP ranges defined by RFC 1918. Class A uses 10.0.0.0 to 10.255.255.255. That's a /8 network. Class B covers 172.16 to 172.31, a /12 block. And Class C ranges from 192.168.0 to 192.168.255, a /16. These are the only private ranges you can safely use inside local networks. Here's how private IP addresses work in real life. At home, your router's LAN might be 192.168.0.1, with your devices ranging up to .254. Hides all of them behind a single public IP. In corporate networks, you might see 10.20.10.0 for marketing and 10.20.20.0 for IT, all private and routed securely through our VPN tunnels. Here's a quick comparison between public and private IP addresses. The difference is simple. Public addresses are globally unique and routable on the internet, while private addresses exist only inside local networks. Private addresses are free to use, reusable across organizations, and rely on NAT for internet access. Beyond the private ranges, a few IPv4 blocks have special purposes. For example, 127.0.0.1 is the loopback address. 169.254.0.0 is a PIPA, used when DHCP fails, and 224.0.0.0 is reserved for multicast. These are not private or public, just special. Section 1.8. Configure and verify IPv6 addressing and prefix. IPv4 has served the internet for decades, but its 4.3 billion addresses just aren't enough anymore. IPv6 fixes that, with 128-bit addresses, giving us an almost unlimited number of unique IP addresses. It also improves performance, with faster packet handling, built-in IPsec security, automatic address configuration, and more efficient routing. Most networks today use a dual-stack model, running IPv4 and IPv6 side by side during the transition period. An IPv6 address is 128 bits long, written in 8 groups of 4 hexadecimal digits separated by colons. Each group, or hextet, equals 16 bits. IPv6 is case-insensitive, supports zero compression, and is designed for efficient, hierarchical routing. Each interface can have multiple addresses. For example, link local, global, or unique local. To read or calculate IPv6 values, remember that every hex digit equals 4 bits. For instance, the hex value A converts to binary as 1010 and F as 4 ones. 9ACF is one 16-bit hextet, and when you stack 8 of them together, you get the full 128-bit IPv6 address. IPv6 addresses can be long, but you can make them shorter. First, drop any leading zeros inside each group. Second, replace one block of consecutive zero groups with a double colon. You can only use the double colon once, otherwise, the address becomes ambiguous. This keeps IPv6 addresses readable without changing their meaning. Here's an example. Step 1. Remove the leading zeros. Step 2. Replace a sequence of consecutive zeros with a double colon. That gives you 2000 $10010, or 2000 0001 $10. But not 2000 $1 10, because 2 double colons would make it invalid. To expand an address that uses a double colon, count how many hextets are written and subtract from 8. The missing number equals how many zero groups the double colon represents. For example, in 2001, DB8 1, 3 hextets are shown, so double colon replaces 5 groups of zeros. IPv6 uses prefix links instead of subnet masks. The prefix defines how many bits belong to the network part. Common examples: /48 for enterprises, /56 for small sites, and /64 for LAN subnets. The network prefix identifies which subnet an address belongs to, just like the network portion in IPv4. It's usually assigned by an ISP or an administrator and is used by routers for forwarding and route summarization. The interface ID is the host portion of an IPv6 address. It's usually 64 bits long and must be unique within the subnet. It can be created automatically with EUI64, generated randomly for privacy, or configured manually. Neighbor Discovery uses it to communicate locally between devices. Here's how IPv6 splits an address into the network portion and the interface ID. The prefix length, like /64, tells us how many bits belong to the network. Each hextet equals 16 bits, so 64 divided by 16 gives 4 hextets for the network. In our example, the first 4 hextets, 2001 DB8ACAD1, are the network prefix, and the last 4, :1, form the interface ID. When expanded, the 64 bits for the network and 64 bits for the interface ID, that's the standard IPv6 structure used in almost every LAN subnet. Subnetting in IPv6 is simple. Just increase the prefix length. Each extra bit doubles the number of subnets and halves the number of hosts per subnet. For example, subnetting /48 into /64 gives 65,536 subnets, each with 2 to the 64th power possible hosts. That's about 18 quintillion addresses per subnet. IPv6 addresses can be assigned in 3 main ways: manually, using DHCPv6, or using Slack. Let's go through each one. In manual configuration, both the prefix and interface ID are set by the admin, just like static IPv4 addressing. It's common for routers and servers where the IP shouldn't change. Always include a prefix, like /64, at the end of the address. Don't worry about the commands yet. This video focuses on the theory part of the exam. For now, just remember the key terms. We'll go through the commands and hands-on labs in a separate session. EUI64 automatically generates the host portion from the device's MAC address. The key command is simply adding a prefix and the keyword EUI-64. This gives a consistent, semi-automatic address based on the interface hardware. Some operating systems instead use random interface IDs for privacy. Slack lets devices configure themselves automatically. They listen for router advertisements, learn the network prefix, and create their own interface ID, usually using EUI-64 or a random value. They then run duplicate address detection to make sure no one else is using that address. The command is IPv6 address autoconfig. With stateful DHCPv6, the server assigns both the IPv6 address and extra details like DNS and domain information, keeping a record of the clients. The command for stateful DHCP is IPv6 address DHCP. In stateless mode, the device builds its address using Slack and only asks DHCP for extra info. To check IPv6 configuration, use ping to test reachability, traceroute to trace the path, or telnet to test a specific TCP port over IPv6. Make sure each interface has a link local address, that global prefixes are correct, and that neighbor discovery works properly. If communication fails, double-check the prefix, link local address generation, and NDP operation. Again, don't worry about the commands yet. For now, just remember the terms. We'll go through the commands and hands-on labs in a separate session. Section 1.9. IPv6 address types. IPv6 groups addresses into three main types: unicast, multicast, and anycast. Unicast sends packets one-to-one, from a single source to a single destination. Multicast sends one-to-many. Every device that joins that multicast group receives the packet. Anycast sends one-to-nearest. The same address can exist on several devices, but only the closest one replies. IPv6 doesn't use broadcast at all. Multicast and anycast replace that function, making the network more efficient. A unicast address identifies a single interface. Packets go straight from one device to another, just like normal host communication between clients or routers. Each unicast address is unique across the network. For example, 2001 DB8 ACAD1:10 delivers only to that one host. These are what you'll use for regular end-to-end communication. Multicast identifies a group of interfaces, usually across multiple devices. It's a one-to-many delivery method. IPv6 uses multicast instead of broadcast for things like neighbor discovery, routing updates, or video streaming. For example, FF02:1 targets all IPv6 nodes on the local link, and FF02:2 reaches all routers on the local link. Anycast addresses are assigned to several interfaces, often on different devices, but only the nearest one responds. It's a one-to-nearest delivery, great for load balancing or redundant services like DNS or web servers. A DNS anycast address, for instance, will always connect you to the closest available DNS server. Again, IPv6 doesn't broadcast. Multicast and anycast handle that role. IPv6 supports several address types, each with a specific purpose. Global unicast starts with 2000 and has a /3 prefix, is publicly routable. Unique local starts with FC and uses a /7 prefix. It's private and used inside organizations. Multicast starts with FF and uses a /8 prefix. It's for one-to-many communication. Link local starts with FE and has a /10 prefix. It's auto-assigned for local communication. Anycast shares one address across multiple devices, delivering packets to the nearest one. Loopback :1 is for internal testing, and unspecified is used before a device has an address. Unlike IPv4, an IPv6 interface can have multiple addresses at once. Each interface always has one link local address, automatically created, one or more global or unique local addresses for external communication, and several multicast memberships for discovery and routing. This design gives IPv6 flexibility. A single interface can talk to local devices, the internet, and multicast groups all at the same time. Modified EUI64 is a method that lets a device build its own interface ID automatically from its MAC address. It works by splitting the 48-bit MAC in half, inserting FFF and an E in the middle, and flipping the 7th bit of the first byte. This method ensures every interface ID is unique while keeping the address predictable. It's widely used for automatic configuration through Slack or manual prefixes with the EUI-64 keyword. Here's how we convert a 48-bit MAC address into a 64-bit interface ID using modified EUI64. Step 1. Split the MAC into two halves. The first half is 001A2B, and a second one is 3C4D5E. Step 2. Insert triple F and an E in the middle. That gives you 001A2B triple FE 3C4D5E. Step 3. Flip the 7th bit of the first byte. The original first byte is 00, which in binary is all zeros. Flipping the 7th bit turns it into 02, so the final interface ID becomes 021A2B triple FE 3C4D5E. Routers periodically send router advertisement messages to the multicast address FF02:1, which means all nodes. The RA includes the network prefix, prefix lifetime, auto configuration flags, and the default gateway. Remember, in IPv6, the default gateway is always learned through RA, not through DHCP. These messages tell hosts whether to use Slack, stateless DHCP-v6, or stateful DHCP-v6 to configure themselves. When a host first joins the network, it doesn't want to wait for the next periodic advertisement, so it sends a router solicitation to FF02:2, the all routers multicast address. This asks routers to reply immediately with an RA message, so the host can configure its IPv6 address right away. Usually, a host sends a few RS messages at startup. Neighbor Discovery Protocol, or NDP, replaces ARP in IPv4. It uses ICMP version 6 messages for discovering other devices, learning MAC addresses, detecting duplicates, and finding default gateways automatically. NDP uses messages such as neighbor solicitation, neighbor advertisement, router solicitation, and router advertisement. All of this happens through multicast instead of broadcast, making IPv6 communication much more efficient. Section 1.10. Verify IP parameters for client OS. OSI model, or Open Systems Interconnection model, is the foundation for understanding how network communication works. It breaks everything into 7 layers, from application down to physical. Each layer serves the one above it and handles its own specific tasks, like addressing, routing, or delivery. We don't actually implement OSI directly, but we use it as a guide to troubleshoot problems logically, one layer at a time. Here's a quick look at all 7 OSI layers from top to bottom. At the application layer, we have user-facing services like HTTP, DNS, and DHCP. The presentation layer handles data format and encryption, things like SSL or TLS. The session layer manages communication setup, while transport ensures reliable delivery with TCP or UDP. At Layer 3, the network layer uses IP for routing. Layer 2 handles MAC addresses and Ethernet framing, and Layer 1 covers the physical media, your cables and network cards. The TCP/IP model is the real working framework behind every modern network, including the Internet. Unlike the OSI model, it has just 4 layers: application, transport, Internet, and network access. It's simpler, protocol-focused, and built around the Internet protocol itself. This model defines how data moves end-to-end across networks using protocols you already know, like TCP, IP, UDP, DNS, and DHCP, the ones that make the Internet actually work. Now, let's compare them side by side. The OSI model has 7 layers, while TCP/IP combines those into 4. The top 3 OSI layers, application, presentation, and session, are grouped into the TCP/IP application layer. Transport maps directly to transport, and the bottom 3, network, data link, and physical, fit into Internet and network access. So, OSI helps us understand concepts, while TCP/IP shows us how networks actually work. Here's how the OSI and TCP/IP layers interact. When data moves down the stack, each layer adds its own header. That's called encapsulation. At the sender side, it starts as application data, becomes a TCP segment, then an IP packet wrapped inside an Ethernet frame, and finally turns into bits on the wire. At the receiver's end, the process reverses. That's decapsulation, stripping off each header until the user sees the original data. Now let's talk about DHCP, the Dynamic Host Configuration Protocol. DHCP automatically assigns IP addresses and other network parameters to hosts, saving you from configuring every device manually. It works at the application layer and uses UDP ports 67 and 68. The process follows 4 steps: discover, offer, request, and acknowledge, often remembered as DORA. On Cisco devices, you can enable DHCP on an interface with the command IP address DHCP. And when a DHCP server is set up on a router, it can dynamically assign IP addresses to clients across the LAN. Next up is DNS, the Domain Name System. DNS is like the Internet's phone book. It translates easy-to-remember names like Cisco.com into IP addresses that computers actually use to communicate. DNS runs on UDP port 53 for regular queries and TCP 53 for zone transfers. On Cisco iOS, we enable it with IP domain lookup and specify a DNS server using IP nameserver. When you ping a host name, the router will first contact that DNS server to resolve the name to an IP. If resolution fails, you can verify the cache using show hosts. That's the iOS equivalent of NSLookup on Windows. A MAC address, or Media Access Control Address, is the unique hardware ID built into every network interface card. Think of it as the hardware fingerprint for the device. It operates at Layer 2, the data link layer, and helps switches deliver frames to the right device inside a LAN. Each MAC address is 48 bits, written in hexadecimal. The first half identifies the manufacturer, and the second half identifies the specific device. It's stored permanently in the NIC and used only for local delivery within the same network segment. Routers use ARP to map IP addresses to MACs, so when one device wants to reach another locally, it sends a frame directly to that MAC address. The default gateway is the router interface that connects your local network to other networks or the internet. It's usually the first or last usable IP in the subnet, and it can be assigned manually or automatically through DHCP. If a destination isn't local, the host sends the packet to the gateway's MAC address for forwarding. In Cisco iOS, you can set it with the command IP default-gateway, which is the router interface IP address on your local network. If that gateway is misconfigured, you'll lose external connectivity even if your local IP looks fine. You can confirm reachability by pinging the gateway first. It's always the first test in any troubleshooting workflow. A loopback address is a special reserved IP that lets a host test its own TCP IP stack without touching the physical network. It works at Layer 3, the network layer, and is typically 127.001 for IPv4, or :1 for IPv6. When you ping the loopback address, the packet never leaves the device. It loops internally through all protocol layers, confirming that the TCP IP stack is installed and functioning correctly. A PIPA, or Automatic Private IP Addressing, is what happens when a DHCP server can't be reached. Instead of staying offline, the device assigns itself an address in the 169254 range. This allows limited local communication within the same subnet, but there's no default gateway or DNS, so it can't reach external networks. Once DHCP becomes available again, the device automatically replaces the address with a valid one. In Windows, all verification happens through simple command line tools. Start with ipconfig/all to view the complete configuration like IP, mask, gateway, DNS, and MAC. If DHCP fails, use ipconfig/renew to request a new lease. Test connectivity using ping, first your gateway, then an external IP, and finally, a hostname to check DNS. If you need to trace the path, trace-RT lists each hop, while NSLookup checks DNS resolution directly. What's different from other systems is the command structure. Each task, like renewing or releasing DHCP, uses a separate switch. Mac OS uses the same Unix foundation as Linux, but its commands look a little different. ifconfig shows your IP and interface details, similar to ipconfig on Windows, but with extra technical flags. For testing, ping and traceroute work exactly the same, though traceroute defaults to UDP instead of ICMP. In Linux, the goal is the same: verify addressing, routing, and connectivity. But the tools are more flexible. You can use IPADR show or the older ifconfig to see interface info, and IP route show to confirm your gateway. Ping and traceroute behave just like on Mac OS, but Linux offers more control. You can specify interfaces, protocols, or packet sizes. So, while the purpose is identical, Linux gives you far more depth and customization. Cisco iOS commands follow the same logic, but from the network device's point of view. Instead of ipconfig or ifconfig, you use show IP interface to verify addresses and interface states. Ping and traceroute work the same way as on Windows or Linux, but iOS adds per-hop response times and extended options for testing paths. So while the tools are consistent across all platforms, Cisco adds the professional-grade depth for real network diagnostics. When something doesn't work, always go layer by layer. If there's no link light or Wi-Fi, that's a layer 1 issue. Check cables or interface status. If the interface is up but you can't reach other devices, check the MAC table or ARP entries. That's layer 2. If you can ping locally but not outside your subnet, inspect your gateway and routing. That's layer 3. If IP works but name resolution fails, it's a DNS issue at layer 7. And finally, if everything works except remote access, check ACLS, SSH configuration, or firewall rules. Always verify in this order: IP, gateway, DNS, path, port. Here, we take that same layer-by-layer logic and apply it to real symptoms. If you see no network access, think layer 1, check cables or Wi-Fi. An interface showing down/down points to a physical or duplex mismatch. A 169.254 address means DHCP isn't reachable, while a duplicate IP is a layer 3 conflict. If you can ping by IP but not by name, that's a DNS problem at layer 7. And if SSH or Telnet fails, the service might be blocked or disabled. Each issue here maps to its OSI layer, and the commands beside it, like ipconfig/renew or show IP route, tell you exactly how to confirm and fix it. Section 1.11, Wireless Principles. Wireless networking lets devices communicate without physical cables by using radio waves. The technology is built on IEEE 802.11 standards, which define how Wi-Fi operates across different frequency bands. With wireless, users gain the flexibility to move around while staying connected, and businesses reduce the amount of cabling required. The goal is to deliver reliable network access with mobility, convenience, and cost efficiency. Wireless technologies are organized by how much area they cover. WPANs handle very short distances, such as your Bluetooth headset. WLANs extend a local network across a building using Wi-Fi access points, and WMANs stretch connectivity across a city or between buildings using outdoor wireless links. Understanding these categories helps you choose the right technology for the right distance and use case. A wireless personal area network is designed for communication within just a few meters. It relies on technologies like Bluetooth, NFC, and Wi-Fi Direct to connect personal devices such as headsets, printers, and keyboards. These technologies often replace short cables, and they commonly operate in the 2.4 GHz ISM band. WPANs are ideal for simple, low-power, close-range connections. A wireless LAN provides network access across medium distances such as offices, classrooms, and homes. Built on IEEE 802.11 Wi-Fi standards, it uses access points connected to a wired backbone to extend the LAN. WLANs allow laptops, phones, and IoT devices to stay mobile without losing connectivity. In enterprise networks, WLAN controllers and lightweight access points manage Wi-Fi centrally for consistency and reliability. A wireless metropolitan area network connects locations across wide areas such as cities or large campuses. These links often use point-to-point or point-to-multipoint antennas to bridge buildings where cabling isn't practical. Organizations choose WMAN technologies to connect warehouses, remote buildings, or outdoor spaces at lower cost than laying fiber. It's essentially wireless used as a metropolitan-scale backbone. Wi-Fi communication depends on three radio properties: amplitude, frequency, and wavelength. Amplitude controls signal strength, while frequency determines coverage and how well the signal penetrates walls. Higher frequencies, like 5 or 6 GHz, offer faster speeds but shorter range. Wavelength ties everything together by describing how the wave behaves in the environment. These fundamentals influence how we design wireless networks. When an AP transmits at high power but a client device transmits at low power, a mismatch occurs. The client may hear the AP clearly, while the AP barely receives the client, causing unstable connectivity. Beyond power levels, coverage is also affected by antenna type, walls, noise, and even humidity. These factors explain why signal bars don't always tell the full story about connection quality. Antenna design influences how Wi-Fi signals spread. Omnidirectional antennas provide 360-degree coverage and are ideal for general indoor use. Directional antennas focus energy in one direction, making them perfect for long-distance links. Patch and panel antennas offer controlled coverage in hallways or rooms. Understanding antenna patterns helps ensure coverage where users actually are. Radio signals behave differently based on what they encounter. Walls and dense materials absorb RF energy, reducing signal strength. Smooth surfaces like metal cause reflections and multipath, which can distort the signal. Refraction bends signals when they pass through materials like glass or liquids. These behaviors explain why wireless performance can vary dramatically from room to room. The 2.4 GHz band is crowded, not just with Wi-Fi devices, but with many household appliances. Microwave ovens, baby monitors, RF cameras, and even fluorescent lighting can disrupt Wi-Fi signals. Because these devices don't follow Wi-Fi rules, their interference can be severe and unpredictable. Knowing these sources helps you troubleshoot issues that appear random, but are caused by non-Wi-Fi transmitters. Wi-Fi operates in unlicensed spectrum, meaning many devices share the same airspace. When too many devices compete, signals overlap and cause collisions, similar to traffic congestion. This is why careful channel planning is essential, especially in busy environments. Understanding how shared frequencies work helps explain why performance drops when the spectrum is crowded. Wireless standards are defined by IEEE, but power limits and frequency access are regulated by FCC, ETSI, and other regional bodies. These rules prevent interference and ensure devices operate safely. Depending on your country, some Wi-Fi channels may be restricted or require additional measures like DFS. Always consider regulatory requirements when designing or deploying wireless networks. Here, we're looking at how Wi-Fi has evolved across the different 802.11 standards. The very early versions, like 802.11b and G, ran only in the 2.4 GHz band and offered relatively slow speeds. Then 802.11a introduced 5 GHz, which gave us a cleaner spectrum but slightly shorter range. With 802.11n, we finally got dual-band support and a big jump in performance thanks to MIMO. From there, 802.11ac focused entirely on 5 GHz and pushed Wi-Fi into the gigabit era. And the latest version, 802.11ax, also known as Wi-Fi 6, brings major efficiency improvements, with Wi-Fi 6E extending those benefits into the new 6 GHz band for even more capacity. Each Wi-Fi generation, from 802.11b to 802.11ax, improves speed, efficiency, and reliability. Lower frequencies like 2.4 GHz travel farther but suffer more interference, while higher bands like 6 GHz offer clean spectrum with shorter range. Measurements such as RSSI and SNR help us assess signal quality, and factors like walls, placement, and antenna type influence overall performance. The 2.4 GHz band provides long-range, wall-friendly coverage, but is crowded and limited to 3 non-overlapping channels. Because channels overlap heavily, wide channels like 40 MHz are not recommended. This band works best for low-bandwidth devices, sensors, and older clients. Its strength is coverage, but capacity and interference are major limitations. The 5 GHz band offers more channels, cleaner spectrum, and support for wide channels such as 40 and 80 MHz. This makes it ideal for high-throughput applications and dense office environments. Some parts of the band require DFS to avoid radar systems, which may cause channel changes. Although the range is shorter than 2.4 GHz, performance and reliability are significantly better. The 6 GHz band, introduced with Wi-Fi 6E, provides an entirely new, clean spectrum free from legacy devices. It supports many non-overlapping channels and wide channels up to 160 MHz for multi-gigabit speeds. Only Wi-Fi 6E devices can use it, which reduces interference. The trade-off is shorter range and more sensitivity to obstacles, but the performance benefits are huge. Different WLAN modes define how devices communicate. Ad hoc mode enables direct client-to-client links, but does not scale. Wi-Fi Direct improves this by adding security and service support. Infrastructure mode, the most common approach, uses APs to coordinate access and roaming. Mesh networks extend coverage without cables, and workgroup bridges connect wired devices to wireless networks. WLAN architectures vary in how they handle configuration, security, and control, and each model fits different deployment sizes and requirements. We'll compare autonomous access points, controller-based lightweight APIs, and modern cloud-managed solutions to understand how each approach delivers wireless connectivity. An autonomous AP operates entirely on its own and performs all Wi-Fi functions locally. It manages authentication, encryption, channel selection, and VLAN mappings without a controller. This model is easy to deploy but hard to manage at scale, since each AP must be configured individually. It suits small environments with just a few access points. A lightweight AP relies on a central wireless LAN controller to manage configuration, security, and RF optimization. The AP handles real-time tasks, while the WLC controls policies and channel/power decisions. This model enables fast roaming, consistent configuration, and easy management across many APs. It is the default choice for medium to large enterprise deployments. Cloud-managed APIs store configuration and monitoring data in the cloud instead of an on-site controller. They pull their settings automatically once online, making deployment extremely simple. The cloud dashboard offers real-time visibility and centralized control across distributed locations. Traffic typically stays local, while only management traffic reaches the cloud. This approach is ideal for retail, schools, and branch networks. In local mode, all client traffic is tunneled back to the WLAN controller, allowing centralized policy enforcement and consistent security. Flex Connect mode is designed for branch sites, where the AP can switch traffic locally and continue operating even if the WAN link to the controller fails. The choice of mode depends on network topology, WAN reliability, and desired control level. The SSID is the wireless network name that users connect to. APIs broadcast SSIDs in beacon frames and can host multiple SSIDs mapped to different VLANs. Using meaningful names helps users select the right network, while VLAN mapping separates traffic for corporate, guest, or IoT devices. Hidden SSIDs provide no real security and can even create additional risks. When an AP joins a controller, it must discover it first. DHCP option 43 can point the AP to the correct WLC IP address, while DNS discovery provides a fallback using a predefined hostname. Accurate time is also critical. If the WLC and AP clocks differ, certificate validation may fail, preventing the AP from joining. These mechanisms ensure smooth AP onboarding. Wireless security begins with authentication and encryption. Authentication verifies who is connecting, using passwords, certificates, or tokens. Encryption protects data as it travels over the air. Legacy methods like WEP and TKIP are insecure, while modern networks rely on AES-CCMP for confidentiality. These fundamentals form the basis of secure Wi-Fi. WPA and WPA2 introduced major improvements in wireless security. WPA used TKIP as a security patch, but WPA2 established AESCC-MP as the industry standard. Both support personal mode with a pre-shared key and enterprise mode with 802.1x authentication. WPA2 remains widely deployed and provides strong security when paired with complex passwords or radius-based authentication. WPA3 enhances wireless security by improving authentication and adding protection against modern attack methods. Personal networks use SAE, which prevents offline password cracking. Enterprise networks gain mandatory protected management frames and optional 192-bit encryption. WPA3 also improves public Wi-Fi through OWE and introduces DPP for secure IoT onboarding. These upgrades make WPA3 far more resilient. Open networks allow users to connect without a password, but traditionally this meant no encryption at all. With WPA3, OWE adds automatic encryption, so each client gets a unique key, preventing other users on the same network from eavesdropping. It still doesn't authenticate the user, but it protects the data in transit in places like cafes and airports. For IoT devices, DPP simplifies secure onboarding by using QR codes or NFC to deliver credentials out of band, making enrollment easier and more secure. 802.1x provides enterprise-grade access control by integrating Wi-Fi with AAA services. When a client connects, the AP or WLC acts as the authenticator and forwards credentials to a radius server. The server validates the user and assigns appropriate permissions, generating unique encryption keys per session. Compared to PSK, 802.1x offers stronger security, better scalability, and identity-based access. Best practices for securing Wi-Fi focus on using strong encryption and modern authentication. WPA2 with AES is the absolute minimum, and WPA3 should be used whenever possible. Avoid outdated methods like WEP or TKIP as they are easily broken. Combining strong encryption with 802.1x authentication and proper key management provides a robust security foundation. Section 1.12. Virtualization Fundamentals. Virtualization is all about taking a single physical machine and breaking it into multiple independent virtual machines that share the same hardware. Instead of dedicating one server to one workload, you can run many workloads side by side, each inside its own VM with its own operating system and resources. This dramatically improves efficiency and reduces the amount of physical equipment you need. It also gives you flexibility. VMs can be moved, copied, backed up, or restored easily because they exist as software-based instances rather than physical boxes. There are a few different ways virtualization can be implemented behind the scenes. Full virtualization is the most common, where the guest OS thinks it's running on real hardware, even though everything is emulated by the hypervisor. Partial virtualization exposes some hardware directly, reducing overhead but requiring some OS awareness. And para-virtualization takes that a step further by allowing the OS to communicate directly with the hypervisor using optimized calls. These different approaches give you different trade-offs between performance, compatibility, and efficiency. A hypervisor is the core component that makes virtualization possible. It sits directly on the hardware or on top of a host operating system, and it creates and manages virtual machines. It allocates CPU, memory, storage, and network resources to each VM and ensures that each one remains isolated from the others. The hypervisor also gives you features like snapshots, cloning, and live migration. Essentially, the hypervisor is responsible for coordinating all of the virtual hardware and keeping your environment stable and efficient. There are two categories of hypervisors. Type 1, or bare metal hypervisors like VMware ESXi and Microsoft Hyper-V Server, run directly on the hardware and are used in production data centers because they offer high performance and stability. Type 2 hypervisors sit on top of a host operating system like VirtualBox or VMware Workstation. These are perfect for labs, testing, and development. Both types support virtualization, but they're used in different environments depending on whether you need enterprise-grade performance or a simple, flexible test setup. A virtual machine is basically a full computer running inside another computer. It has its own operating system, applications, virtual CPU, RAM, storage, and network interfaces. From the VM's perspective, everything looks like dedicated hardware, but in reality, the hypervisor provides all the virtual components. VMs are completely isolated from each other, which makes them secure and stable. And because a VM is stored as a set of files, it's incredibly easy to move, back up, copy, or restore, making virtualization far more flexible than physical servers. Containers are a lighter-weight alternative to virtual machines. Instead of running an entire operating system for each instance, containers share the host's OS kernel, but keep applications isolated from each other. They start very quickly, use fewer resources, and are ideal for cloud-native environments where you need to deploy and scale applications rapidly. Tools like Docker and Kubernetes make it easy to package code with everything it needs and run it consistently across different environments. Containers and VMs both provide isolation, but they do so in different ways. VMs virtualize hardware and run full operating systems, which gives strong isolation and compatibility with almost any OS. Containers, on the other hand, virtualize only the application environment, so they're much smaller and faster to start. VMs are great for infrastructure and long-running workloads, while containers excel in modern application development, microservices, and environments where frequent updates or rapid scaling are required. Most organizations use both technologies depending on the workload. Virtual networking provides all the connectivity needed within a virtualized environment. The hypervisor creates virtual switches, virtual NICs, port groups, and uplinks so virtual machines can communicate just like they would on a physical network. You can assign VLANs, apply policies, isolate workloads, and control traffic, all from software. This makes networking inside a virtual environment incredibly flexible, scalable, and easy to modify without touching physical hardware. A virtual switch works just like a physical Ethernet switch, except it's entirely software-defined. It connects VMs to each other and to the external network through physical uplinks. It understands MAC addresses, supports VLAN tagging and trunking, and applies security or traffic policies based on the port group configuration. Because it's virtual, you can instantly reconfigure, clone, or expand your switching environment. Popular implementations include VMware vSwitch, VMware Distributed Switch, Hyper-V Virtual Switch, and Open vSwitch. A virtual NIC is the network interface a VM uses to communicate. It behaves like a physical NIC, complete with its own MAC address and VLAN tagging capabilities, but it's created and managed by the hypervisor. You can connect a VNIC to different port groups, add additional VNICs for multi-homing, or reconfigure them without restarting the VM. Modern virtual NICs, such as VMXNet3, are optimized for performance and integrate tightly with the hypervisor's networking stack. NFV moves traditional network appliances like routers, firewalls, and load balancers into software that runs on standard servers. Instead of buying dedicated hardware, you deploy a virtual router or firewall as a VM or container. This approach is incredibly flexible and cost-effective because you can scale services up or down quickly, deploy them wherever needed, and automate their configuration. NFV is widely used in cloud environments, service provider networks, and modern enterprise data centers. AVRF allows a single router or switch to maintain multiple independent routing tables at the same time. Each VRF acts like a separate virtual router with its own interfaces and routes. This is extremely useful for segmenting networks, supporting multiple customers, or handling overlapping IP address ranges. VRFs are essential in MPLS networks, multi-tenant environments, and large enterprises where traffic separation and security are critical. Virtual storage abstracts multiple physical disks and storage systems into logical storage pools that virtual machines can use. Instead of being tied to a specific physical disk, a VM sees a virtual disk located on shared storage. This enables high availability, live migration, and clustering because VMs can run on different hosts while accessing the same data store. Virtual storage also supports thin provisioning, snapshots, and replication. features that make management easier and storage usage more efficient. ASAN provides block-level storage over dedicated high-performance networks like Fibre Channel. To the server, SAN storage looks like a local disk and is ideal for demanding workloads like databases and virtualization clusters. NAS provides file-level storage over standard Ethernet using protocols like NFS or SMB, making it perfect for file sharing, backups, and user directories. Both play important roles, but SAN is optimized for performance and low latency, while NAS focuses on accessibility and simplicity. Cloud computing relies heavily on virtualization. Cloud providers pool vast amounts of compute, storage, and networking resources and use virtualization to carve them up into on-demand services. This makes cloud environments scalable, automated, and highly resilient. When you spin up a VM on AWS, Azure, or Google Cloud, virtualization is working behind the scenes to allocate resources, isolate workloads, and ensure high availability. Virtualization is essentially the engine that powers the cloud. IaaS gives you virtual machines, virtual networks, and scalable storage directly from the cloud. You control the operating systems, applications, and security settings, while the provider manages the underlying hardware and hypervisors. This model is perfect for lift and shift migrations, running servers without owning physical hardware, and building flexible, scalable environments. Common examples include AWS EC2, Azure Virtual Machines, and Google Compute Engine. PaaS provides a fully managed platform where you can build and deploy applications without worrying about the underlying servers. The cloud provider handles the operating system, runtime, scaling, security updates, pretty much everything except your code and data. It's ideal for developers who want to focus on building applications rather than managing infrastructure. Examples include Azure App Service, Google App Engine, and serverless offerings like AWS Lambda. SaaS delivers complete applications over the internet, fully managed by the provider. You don't manage servers, storage, or even the platform. Everything is handled for you. Users just log in and start working. SaaS covers things like email, collaboration tools, CRM systems, and productivity apps. Popular examples include Microsoft 365, Google Workspace, Salesforce, Zoom, and Slack. It's the simplest cloud model from a management perspective. Section 1.13. Switching Concepts. When we look at how switches operate, everything begins with the Ethernet frame. This is the basic data unit traveling across the LAN. The switch isn't analyzing IP addresses yet. It's focused on specific Layer 2 fields inside the frame, like the source MAC, destination MAC, and the type/length field. Frames also have a minimum and maximum size and include an FCS at the end, which allows the switch to detect errors. If the FCS doesn't match, the frame is simply dropped. Understanding this structure helps explain why switches forward some frames, filter others, and flood the rest. In Ethernet, every frame you see falls into one of three traffic types: unicast, broadcast, or multicast. Unicast traffic is straightforward. It's one device sending directly to another, and the switch uses its MAC table to forward it. Broadcast is delivered to every device on the same network segment, and you see it in things like ARP or DHCP. Multicast is meant for a group of devices, such as streaming or discovery protocols. Early on, switches treat multicast a lot like broadcast until additional features refine it. Knowing these three types helps you predict how the switch will forward each frame. A collision domain is simply the area where two devices could transmit at the same time and interfere with each other. This was common with hubs, where everyone shared the same medium. Modern switches change that completely by giving each port its own collision domain. That means devices can send and receive independently, especially when operating in full duplex. If you ever see late collisions or errors, that often points to a duplex mismatch or cable issue. Understanding collision domains is key to seeing how switches improve performance compared to old shared media networks. Let's imagine a small network that originally used a hub. With the hub, all devices shared one big collision domain, so whenever two PCs transmitted at the same time, their signals collided and they had to retry. After replacing the hub with a switch, Each device now connects to its own dedicated port. That immediately eliminates collisions and allows full duplex operation. Traffic on one port no longer interferes with traffic on another. This simple upgrade dramatically increases reliability and overall network performance. A broadcast domain defines how far a broadcast frame can travel. When one device sends something like an ARP request, every other device in the same broadcast domain receives it. Switches forward these broadcasts out every port except the one they arrived on. Routers, on the other hand, stop broadcasts. They don't pass them along, which creates the broadcast boundary. Because every device has to process each broadcast, too many broadcasts can affect performance. Unknown unicast traffic also stays within this same boundary until the switch learns where the destination lives. A VLAN creates a logical separation inside a switch, allowing you to divide one physical network into multiple independent Layer 2 networks. Devices in the same VLAN share a broadcast domain, while devices in different VLANs are fully isolated unless routing is involved. VLANs help with organization, security, and controlling broadcast traffic. Each VLAN has an ID, and a switch can support many VLANs at once. When VLANs span multiple switches, tagging keeps their traffic separate. This is the foundation of modern network segmentation. Picture a switch that has 3 different VLANs defined. When PCA in VLAN 10 sends an ARP request, only devices in that same VLAN receive it. In this case, just PCB. Devices in VLAN 20 or VLAN 30 never see that broadcast. The same happens when PCC in VLAN 20 sends a DHCP discover. Only devices in that VLAN respond. This setup keeps each group of devices isolated and prevents unnecessary broadcasts from crossing into sections of the network where they don't belong. The MAC address table is the switch's internal map of where devices are located. It keeps track of which MAC address is reachable out of which interface, so the switch can forward frames directly without flooding the network. This table constantly updates as devices move or reconnect, and it lives in high-speed hardware, so lookups are extremely fast. Without this table, the switch would have to flood nearly everything, so it's a critical part of efficient Layer 2 switching. MAC learning is how a switch builds its MAC address table. Every time it receives a frame, it looks at the source MAC and records which port it came from. This allows the switch to map devices to ports and forward traffic efficiently. Learning happens per network segment, and if a device moves, the entry gets updated automatically. Once the switch knows where devices are, it doesn't need to flood traffic anymore. It can forward frames directly. This dynamic learning process keeps switching fast and accurate. Imagine a switch with several devices connected, but an empty MAC table. When PC1 sends traffic to PC2, the switch sees the frame on its incoming port, learns PC1's MAC, and records it. Because it doesn't yet know where PC2 is, it floods the frame to the other ports in the same segment. PC2 receives it and replies, and that reply allows the switch to learn PC2's MAC as well. From that moment on, traffic between PC1 and PC2 is sent directly between their ports with no more flooding. Frame switching is the core function of a switch. When a frame arrives, the switch checks the destination MAC and looks it up in the MAC table. If there's a match, it forwards the frame only to that specific port. If the destination happens to be on the same port the frame came from, the switch filters it out because forwarding it would be pointless. But if the switch doesn't have an entry, meaning it doesn't yet know where that MAC address lives, it floods the frame. This forward, filter, or flood logic is the foundation of switching. Switching methods describe how quickly a switch processes frames before forwarding them. Store and forward is the most common. The switch receives the entire frame, checks the FCS, and forwards only if it's clean. That makes it reliable and ideal for modern networks. Cut-through is faster because the switch starts forwarding as soon as it reads the destination MAC, but it may forward corrupted frames. Fragment-free is a hybrid that waits for the first 64 bytes to avoid partial collisions. Understanding these methods helps explain the balance between speed and accuracy. Frame flooding happens when the switch doesn't know where the destination device is yet. For example, when a device connects for the first time and no MAC entry exists, the switch sends that frame out every port in the same network segment except the one it came in on. Broadcast frames are always flooded, and multicast frames are initially treated the same way. Once the switch learns the MAC address and associates it with a port, flooding stops and the frame is forwarded directly. Flooding is normal, but too much of it can indicate misconfigurations or network issues. MAC aging keeps the MAC table clean and prevents outdated information from causing issues. Each learned MAC entry has a timer, usually around 300 seconds, and the timer resets every time the switch sees traffic from that device. If a device goes silent or disconnects, its entry eventually expires and the switch forgets it. This frees up space and ensures that if the device reconnects somewhere else, the switch learns its new location correctly. Static entries, on the other hand, never age out. Static and sticky MAC addresses are ways to give a switch more control over which devices are allowed on a specific port. A static MAC is manually assigned and never ages out, making it useful for devices that shouldn't move. Sticky MAC starts as a normal learned address, but becomes fixed to the port after it's learned. Both methods help prevent unauthorized devices from connecting or swapping cables and provide more stable behavior on sensitive ports. MAC flapping happens when a switch sees the same MAC address appearing on different ports. This usually means the device is connected in two places, or there's a loop or misbehaving device on the network. The switch keeps updating the MAC table back and forth, which causes unstable forwarding and can lead to excessive flooding. It's a common symptom of wiring mistakes or accidental loops, and most switches will log a warning when it happens. A MAC table overflow occurs when the switch's MAC address table becomes completely full. This can happen if too many new MAC addresses show up at once, or in worst-case scenarios, through a malicious MAC flooding attack. When the table is full, the switch can't learn new MACs and begins treating unknown unicast traffic as broadcasts. That increases flooding, impacts performance, and can even expose traffic to unintended devices. It highlights why aging and table management are so important. That's it for the complete network fundamentals section. If you prefer quick 10-minute lessons, all the subtopics are available separately. Before moving on, take a quiz to test your understanding. Quizzes, summaries, and slides are available on ccna.academy. If you have any questions, leave a comment below and I'll be happy to help. Thanks for joining, and see you in the next video.